Hey everybody, welcome back to Bite-Sized Statistics. My name is Sean Rose and you are watching the Continuous Outcomes route, Module 1, which covers t-tests, and this is the first video which is going to cover the theory of t-tests. So in terms of the entire organization of this video series, hopefully you're coming from the setup video where we downloaded the Conda package manager and then got set up with an R environment and with Jupyter notebooks. Now we're jumping onto the continuous outcomes route and we're going to start talking about the theory of t-tests. We're also going to talk about how to power t-tests and things like effect sizes. So let's start by talking about how the student's t-distribution even arises. And I'm going to assume you have some familiarity with things like random variables and independent identically distributed and such. So let's consider that we have NIID, independent identically distributed, normal random variables, with mean mu. So this could be, for example, a measurement of the weight of n Siamese cats, and the true mean mu could be the population mean of the weight of all Siamese cats or something. Let's define the random variables, y bar, which is just this sample mean, so the standard sum the y's divided by n, s, which is the sample standard deviation defined in the normal way, and then we're going to define this thing called capital T, which is the t-statistic. And we're going to define that as the sample mean minus the true population mean divided by the sample standard deviation divided by root n. It turns out that capital T has a student's t-distribution with n minus 1 degrees of freedom. So we know, if we know the true mean, we know the distribution of this capital T. And this is going to arise in hypothesis testing because we're going to assume we know the true mean, and then we're going to figure out probabilities using this statistic T because we know its probability distribution function. It also, as an aside, turns out that y bar and s are statistically independent. That's kind of an interesting result, and I'm not going to go into it in too much depth because you don't really need to understand it that well to use the t-test, but if you're interested in that, I suggest you Google Cochran's theorem. That's the easiest way I know to get at that result, at least. So what does a student's t-distribution actually look like? Well, the student's t-distribution has this free parameter, the number of degrees of freedom, so there's a bunch of different student's t-distributions. But the basic idea is as you increase the degrees of freedom, the distribution gets taller and it gets thinner. And as the degrees of freedom goes to infinity, it actually approaches a standard normal distribution. So a normal distribution with mean 0 and standard deviation of 1. And here I've just plotted t-distributions with 4 different values for the degrees of freedom to illustrate that fact. Okay, so now we know where the student's t-distribution comes from, how it can arise in practice, but now let's start talking about what it means to do a hypothesis test. So what is hypothesis testing? Well, in hypothesis testing, we assume some null hypothesis, H naught, to be true, and then we quantify the probability that we would get the measurement we did or something more extreme, and by more extreme, we define that using the so-called alternative hypothesis, H sub A, and this will make a lot more sense once we start getting into some examples. But basic idea behind hypothesis testing is we're going to control the probability of rejecting a true null hypothesis at level alpha. And what we mean by that is if we assume the null hypothesis to be true, so for instance that our variables come from an IID normal distribution with mean 0, we want the probability that we get a result, or the probability that we reject that null hypothesis when the null hypothesis is indeed true, to be equal to some value alpha, which is usually taken to be 5% or 1% or 0.1%. I'm going to typically use 5%. I apologize in advance if I accidentally say 5% instead of alpha in some of the subsequent slides. Note on Verbage, rejection of a true null hypothesis is called a type 1 error. It's also called a false positive because we're typically looking to reject a null hypothesis. We typically have some result. We want to do something like show two means are different, so we assume under a null hypothesis that the means of two populations are the same, and then we look for evidence to reject that null hypothesis. So if we accidentally reject a true null hypothesis, we call it a false positive. We don't, by contrast, control the probability of accepting a false null hypothesis. This is what's called a false negative because in this case the null hypothesis is indeed not true. So for instance the two population means are really different, but we accidentally said that we couldn't conclude that they're different. So we call it a false negative, or also called a type 2 error. Power analysis deals with type 2 errors. Power is defined to be 1 minus the probability of a type 2 error, and we commonly design our studies, if we have an estimate of an effect size, we commonly design our studies to keep the probability of a type 2 error below 20%, or in other words, we try to keep the power of the study above 80%. Okay, so let's actually build a t-test now. So let's say that we want to test the null hypothesis that we are measuring NIID, normal random variables, with mean mu. So for a physical example, let's say we're measuring the weight of n Siamese cats, and we're trying to estimate the true population mean of Siamese cats. And we have some thought of, oh, well, the population mean weight of Siamese cats is 10 pounds. And we want to say, do we have evidence to reject the null hypothesis that the population mean weight of Siamese cats is 10 pounds? So we want to know, is the mean really mu? Is the mean really 10 pounds? Under the null hypothesis, the mean really is 10 pounds. We know the distribution of the t-statistic, y bar minus mu over s blah blah blah. Because we know the distribution of t, we can design tests using that distribution that will accept the null hypothesis with probability 1 minus alpha, and will reject it with probability alpha. And that's exactly what we want. We want to design a test that will only reject a true null hypothesis with probability alpha. Unfortunately, there are infinitely many of such tests, and I'll go into a couple slides from now, I'll go into an example of why that's true. But thankfully, people really only use 3 test designs, because there's really only 3 test designs when you think about it that make that much sense. And those are the 2 one-tailed tests, so the right-tailed and the left-tailed test, and also the symmetric or the two-tailed hypothesis test. So let's start with the one-tailed or right-sided t-test. So in a right-sided t-test, the null hypothesis is the same as always, that the y sub I are IID normal random variables with mean mu naught. The alternative hypothesis is that the true population mean is greater than the mean I'm assuming in the null hypothesis. So in our Siamese cats example, we're assuming the true population mean is 10 pounds. We're looking for evidence that the true population mean of Siamese cats is actually greater than 10 pounds. And we're going to use what we're essentially going to do is we're going to run the experiment, we're going to calculate a t-statistic, and then we're going to look at a threshold on the t-statistic. If the t-statistic is less than a certain value, we're going to accept the null hypothesis, and if the t-statistic is greater than a certain value, we're going to reject the null hypothesis. And we just have to pick that threshold value so that we reject a true null hypothesis with only probability alpha. And the way we can do that is using the so-called cumulative distribution function, which I've denoted by capital F here. It's just the probability of obtaining a t-statistic that's less than or equal to the argument of the function, so in this case lowercase t. So we can define a so-called acceptance region using this threshold. We basically say if our t-statistic is less than this critical t value, we're going to accept the null hypothesis. And if our t value is greater than t critical, we're going to reject our null hypothesis. And we want the cumulative distribution function of t crit to be equal to 1 minus alpha, because we want to accept a true null hypothesis 1 minus alpha % of the time. And because capital F happens to be invertible for a t-distribution, t-crit can be written as being equal to the inverse of f of 1 minus alpha. And the inverse of f is sometimes called the percentile point function or the quantile function, or some people just call it the inverse CDF. I'm denoting it by f to the -1 here. So graphically what this means is we essentially define some critical t value based, which we can calculate using our inverse cumulative distribution function. And then we say, okay, I made my n measurements, I calculate my t-statistic, and if t comes out to be less than that critical value, I don't reject the null hypothesis, so that's the green area in this plot. And if t comes out greater than that critical value, I do reject the null hypothesis, and that's the red area shown in this plot. The red area has area alpha, because I want the probability of rejecting a true null hypothesis to be alpha, and the green area has a probability 1 minus alpha. Again, I want the probability of accepting a true null hypothesis to be 1 minus alpha. So sort of flipping that one on its head, we can also do a one-tailed left-sided t-test. And in this case, the null hypothesis remains the same. The alternative hypothesis is now that the true population mean is less than the population mean I've specified in my null hypothesis. So in our Siamese cat example, I've assumed the population mean is 10 pounds, but I'm looking for evidence that the true population mean is actually less than 10 pounds. And here the logic is essentially the same thing. It's pretty straightforward. We're again going to define a critical t-value, and it turns out that in this case it's the inverse cumulative distribution function evaluated at alpha. And graphically speaking, what that looks like is shown on the right here, where we choose our critical value such that the area in red is alpha. That's the probability of rejecting a true null hypothesis. And the area in green is 1 minus alpha, and that's the probability of accepting a true null hypothesis. The last sort of reasonable variant or reasonable alternative hypothesis that you can do that constructs a hypothesis test at level alpha is to look at the so-called two-sided t-test. And I would argue this is actually the one that you see most commonly. So the alternative hypothesis here is that mu is not equal to the mu naught you've specified in your null hypothesis. So again, our Siamese cat example, we've assumed a true population mean of 10 pounds. Now we're looking for evidence that the true population mean is not 10 pounds. So not 10 pounds in either direction, either greater than or less than 10 pounds. Again, the logic is very similar to the one-sided t-test, but here we're going to specify our acceptance region to be a region of values that is centered around the mean of the t-distribution. So we can again evaluate our critical threshold value using the inverse cumulative distribution function. It turns out it's the inverse CDF evaluated at 1 minus alpha over 2, so that the sum of the red areas in this plot here, the sum of the areas under my two tails, is equal to alpha. And the area under my acceptance region, again, is 1 minus alpha. So again, I have a probability of alpha of rejecting a true null hypothesis, and I have a probability of 1 minus alpha of accepting a true null hypothesis. So you might say, Sean, that's great, you've shown me how to construct a hypothesis test, but you're talking about this like t-statistic and thresholding it and stuff. But in the literature, I always see these things called p-values. So what's a p-value? Well, a p-value is just the probability of getting the measurement you did or getting something more extreme. And the way we define more extreme uses the alternative hypothesis. So what we end up doing is getting a p-value that we can compare to our alpha level, and if p is less than alpha, that means that the null hypothesis was rejected. It's essentially just a number that can be compared to the threshold value, and it means the exact same thing as the t-statistic. It's just a different way of stating it. But the way we would actually calculate a p-value, say for a two-sided alternative hypothesis, is we would do our measurement, get some t-statistic, and I show on the right here, say we measured a t-statistic that is that value. To get the p-value for the two-sided t-test, we integrate over both tails of the t-distribution that are farther away from the mean than that value is, and we sum those areas to get the p-value. So in this plot, the total red area is the p-value. If the p-value is less than 0.05 or alpha, whatever our level of confidence is, we reject the null hypothesis. If p is greater than that value, we accept the null hypothesis. And that can be seen pretty easily to be equivalent to using a threshold on the t-statistic like we talked about in the last couple slides. So the definition of the p-value changes slightly when you walk over to a one-sided alternative hypothesis. So say we're looking at the right-tailed alternative hypothesis, mu greater than mu naught. Then we define the p-value to be just integrating it from our measurement to the right on the t-distribution. So on our plot here, the red area would be our p-value for a measured t-statistic of whatever that measured value is. Again, the alternative hypothesis is just defining what we mean by more extreme when we integrate over values that are more extreme than the t-statistic we measured. And you can, by comparing this to the acceptance region for the one-sided t-test, you can see that the p-value, thresholding the p-value at the level of alpha is equivalent to thresholding the t-statistic at that critical t-value. So I also said earlier that there were infinitely many alpha level tests. And you might be wondering at this point, what the heck did you mean by that? Because you only talked about 3 different hypothesis tests, the two one-sided and the one two-sided. Well, I could also make a hypothesis test where, again, I assume my typical null hypothesis, my y sub I, or IID normal random variables with mean mu naught, But here I could do an alternative hypothesis that's kind of funky, and I'm going to basically just define my acceptance region and my rejection regions by the green and red areas shown on the right. And I can make it so the total area shown in red is alpha, so the sum of those two red areas is alpha, and the sum of the three green regions is 1 minus alpha. And if I run a test where I say I accept the null if my t-statistic is in one of the green regions, and I reject the null if the t-statistic is in one of the red regions, that is an alpha level hypothesis test by definition. Now, it would be tricky to define a p-value for such a test, because what we mean by quote-unquote more extreme when you have that weird rejection region is a little bit tricky. But this is indeed an alpha level hypothesis test. Luckily, it's one that makes absolutely no sense to use in practice, so we don't really have to think about it. So the last thing I want to talk about before we get into the nitty-gritty of actually running a couple t-tests is confidence intervals. And these pop up when we're asking the question of how can we construct an interval estimate of a parameter such that 95% of the time, or 1 minus alpha percent of the time, when we run our experiment, the interval we construct will contain the true value of the parameter mu. So if I'm doing the Siamese cat experiment, I want to be able to take a measurement of n cats and say if I took a measurement of n cats thousands of times, I just did this experiment over and over and over again. Each time I want to be able to construct an interval, and if I ran that experiment over and over and over again, I want that interval I construct to contain the true value of mu in 95% of the experiments. Turns out we can actually do this using the t-statistic. So if we assume our measurements are IID normal with mean mu, as we have the whole time, then we know the distribution of the random variable t, again defined in the normal way, we know that's the student's t-distribution with n-1 degrees of freedom. Better yet, this distribution does not depend on the value of mu. Once we subtract mu off from the sample mean, the t-distribution itself doesn't depend on mu. And this is actually, by definition, we call t what's called a pivotal quantity. It is a function of the measurements, the y sub i's, the parameter of interest, mu, and it is independent. The distribution of the result you get, the t-statistic itself, is independent of the parameter mu, the parameter of interest. So why are pivotal quantities nice? Well, with a pivotal quantity like this, we can actually really easily construct a 1 minus alpha percent confidence interval or a 95% confidence interval. And the way you can do that is say, okay, we'll take the critical t value like we did in the two-sided t-test. So take it to be inverse cumulative distribution function evaluated at 1 minus alpha over 2. By definition, that means that the probability that our t-statistic lies in the interval negative t-crit to positive t-crit is equal to 1 minus alpha. That's literally just the plot from the two-sided t-test that we showed earlier, where the green acceptance region is centered and has area 1 minus alpha. If you just rearrange the internals of that probability here, it turns out that what you get is that the probability of y bar minus t crit times s over root n less than mu less than blah 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 is equal to 1 minus alpha. So what we just did is constructed a 95% or a 1 minus alpha percent confidence interval. Namely, the lower bound is y bar minus t crit times s over root n. The upper bound is y bar plus t crit times s over root n. So this, using that pivotal quantity, the t-statistic, we've constructed a 95% confidence interval, or a 1 minus alpha percent confidence interval more generally. I want to note this is equivalent to finding all of the values of mu for which a two-tailed t-test with null mu not equal to mu would not reject the null hypothesis. Now that's a tricky statement to unpack, but think of it this way. If I ran a hypothesis test using the lower end of my 95% confidence interval as the true mean. So I would run a hypothesis test where my null hypothesis is that the true mean is equal to y bar minus t crit times s over root n. That hypothesis test would just pass, just barely pass, at the alpha level. Similar for the opposite side of the 95% confidence interval. The y bar plus t crit times s over root n, a hypothesis test centered at that value would also just pass, a two-sided, I should say, hypothesis test would also just pass at the alpha level. So it turns out there's actually this duality between confidence intervals and hypothesis tests. If I have a confidence interval, I can construct a consistent hypothesis test. If I have a hypothesis test, I can construct an equivalent or a consistent confidence interval. And it turns out this duality even extends to those crazy hypothesis tests I was talking about before, where the rejection regions were actually not like a single interval, they were just kind of random or weird. But we're not going to talk about that too much. It turns out confidence intervals have to be generalized to confidence sets in that case. They don't have to be intervals. But other than that, it's actually the same exact type of logic. Okay, so at this point you're probably getting a little bit bored because I've just kind of expounded upon random stuff for the last 20 minutes. So now we're going to actually get into the nitty-gritty of what we're trying to do, which is just how to run a t-test. And to do that, we are going to use some verbiage that comes from the chalk chart. So hopefully you are familiar with this already, but if not, please study up. We are going to look at paired and one-sample t-tests first. So a paired or one-sample t-test, that verbiage, paired and one-sample, is interchangeable. They're the same thing. We're going to run a one-sample t-test to investigate, are cats getting chonkier? So our raw data is going to be that we measure the weight of n heckin' chonkers in 2019 and also in 2020. And we're going to denote their weights in 2019 with the second index 1, and in 2020 the second index is going to be 2. The first index is going to index the cat. We're then going to create the measurements y sub I equals y sub I2 minus y sub I1, meaning we take the weight in 2020, we subtract off the weight in 2019, that's our new measurement. We are then going to test the null hypothesis that these y sub I are samples of IID normal random variables with mean 0. We could also test this against some non-zero mean mu, but here we're just going to assume that we're testing that we're interested in whether or not the cats are getting chonkier. So we're just going to test, is there any difference in the means of the two populations, meaning we're going to test the hypothesis that the difference in their weights is 0. So how do we do that? Well, first we define our t-statistic like normal. We do y bar minus 0 in this case, so just y bar divided by s over root n. Y bar is the sample mean, s is the sample standard deviation as before. And under the null hypothesis, we know that t follows a student's t-distribution with n minus 1 degrees of freedom. So we just look at this t-value and we compare it to some critical t-value using either a one or a two-tailed hypothesis test, and that's it. That's a t-test. Okay, but you also may have heard of two-sample t-test. So what's the difference? What is a two-sample t-test and how does it differ from a one-sample t-test? Well, a two-sample t-test looks at the means of two different populations. So say I'm trying to look at the mean weights of two different cat breeds and see if they're different. So I measure n cats from breed 1 and then I measure the weights of m cats from breed 2. And I'm going to look at whether the means of these two, the weights of these two cat breeds are different. So I'm going to test the null hypothesis that the y sub ij are samples of IID normal random variables with a common mean. And I'm actually going to do something that's not really strictly student's t-test. I'm going to use what's called Welch's t-test, which is an approximate, but it's a generalization of student's t-test where you don't have to assume that the standard deviation of the weights of the two breeds is equal. The regular student's t-test, your null hypothesis would assume that all of the y sub ij come from a common normal distribution so that the variance is equal between the two breeds. So how do I actually calculate the t-statistic for Welch's t-test? Well, you define the t-statistic to be the difference in the two sample means. It doesn't matter which sample mean you take first. Here I did the first breed minus the second breed. You could equally as well have done second breed minus first. I divide that by what's called the pooled sample standard deviation, and then I multiply that by root 1 over n plus 1 over m. The pooled sample standard deviation is essentially just replacing the normal sample standard deviation in the one sample t-test. It's just a weighted average of the two sample variances and then take a square root. The root 1 over n plus 1 over m term replaces the root 1 over n term from the one sample t-test. Turns out, if you define t in this way, that under the null hypothesis, t is approximately distributed as students t with degrees of freedom given by the so-called Welch-Satterthwaite, I don't actually know how to pronounce it. Google it. They have an equation. It's kind of ugly, but it gives you the degrees of freedom for a t distribution for which the t statistic you calculated is approximately distributed. You can then use that distribution to run a one- or two-sided hypothesis test, just in the way we've been talking about this entire time. So that actually does it believe it or not, for t-test. That's really all there is to running a t-test. So now let's talk about effect sizes, because these are, in my opinion, just as important as the hypothesis tests themselves. So first thing is that a p-value less than 0.05, or you're able to reject the null hypothesis. That doesn't actually mean that the effect you measured is large. All it means is that you measured an effect that's statistically significant. And statistical significance is not the same thing as a significant or a large measurement. So for example, you may have a really tiny effect. You may have been measuring weights of two different cat breeds, where these two cat breeds, their weights are like 10 pounds and 10.05 pounds. But if you measure the weights of enough cats, guess what? You're gonna see a statistically significant difference in running a t-test. And the reason why you can figure out by looking at the t-statistic itself, as I've shown here. So if you look, let's say the difference between the true population means is like 0.05. Well then, as I take more and more measurements, I expect the numerator in this equation to approach 0.05. The denominator is going to keep getting smaller and smaller because the pooled sample standard deviation is going to approach some constant, whatever the approximate population standard deviation is. But I'm dividing it by root n. So as I take more and more measurements, S sub p over root n is going to get smaller and smaller and smaller. My t-statistic is going to get larger and larger and larger. And eventually I am going to get a t-statistic where I actually reject my null hypothesis. So this is in some sense a bit of a problem, and people have even published papers where they're like the fallacy of p-values, but I don't really think it's a fallacy. I think it's just you have to understand what you're talking about when you're talking about p-values, and you have to accept the fact that if you make enough measurements, you're going to see an effect that's statistically significant no matter how small the size. So the question is, how do we sort of quantify, instead of whether or not we see a statistically significant difference, how do we quantify the size of the effect? And well, of course, effect sizes speak to this. So Cohen's d and Hedges g are two appropriate effect sizes when talking about t-tests. And Cohen's d is really simple. It's related essentially to the t-statistic. You just get rid of the root n in the denominator. It's just difference in sample means divided by pooled sample standard deviation. And you can think of it as like a single signal to noise ratio, but I'm going to hold off on that because it's in the next slide. Hedges g just scales this by a factor and happens to be a less biased estimator for small samples. You can also get 95% confidence intervals on these values. I say it's a tad complicated. It's not really complicated, but R does it for you, so you don't have to think about it, which is really nice. So what about how we interpret these effect sizes? Well, you can think of Cohen's d like a signal to noise ratio. You can also think of Hedges g in the same way. Essentially, it's the number of standard deviations that are separating your two samples. So you can think of it as quantifying how far your two population means are apart in terms of the population standard deviation. So if I measure a Cohen's d of 0.1, then I'm estimating that my two populations means are different by 10% of the population standard deviation, or really that my signal is kind of lost in the noise. Well, not really lost in the noise, but it's small compared to the noise. You can have a tiny Cohen's d, so you can have a small effect and still have p less than 0.05. This just means that you detected a difference that's tiny compared to the noise in your data, which probably means you measured a bunch of data. So that does it for t-tests and effect sizes. What about power? Because at the beginning of this video we talked about the probability of a type 2 error. Well, power is defined as 1 minus the probability of a type 2 error, 1 minus the probability of falsely accepting a false null hypothesis, so accepting a false null hypothesis. To calculate power, we have to assume a true distribution that is different than the null. So typically when we're talking about type 1 errors, we assume the null distribution is true and then calculate probabilities. When we talk about power, we assume some other distribution is true and then calculate the probability that we would falsely accept the null hypothesis. So to do this, we first need an effect size of something like Cohen's d or Hedges g. And this is one reason to report these things in papers, because if you just report a p-value, I can't power a future study. If you report Cohen's d or Hedges g, or even just an estimate of differences between the two population means and a population standard deviation estimate, then I can run a power analysis. So how do we run a power analysis? Well, it's actually not that complicated. So again, let's consider NIID normal random variables with mean, mu, and standard deviation sigma, and let's test the null hypothesis that mu naught, or let's imagine we're testing the null hypothesis that mu naught is equal to some mu that is in fact wrong. So we'll call it mu sub wrong. Turns out that the quantity t defined by sample standard or sample mean minus mu wrong over s over root n follows what's called a non-central t distribution with n minus 1 degrees of freedom and a non-centrality parameter that's equal to root n times mu minus mu wrong over sigma. Don't worry about the details of that. All that matters is that we know how t is distributed given the number of measurements n and given mu minus mu wrong over sigma. And mu minus mu wrong over sigma is just Cohen's d or Hedges g, or if you give me an estimate of mu minus mu wrong over sigma, that is what I need to do a power analysis. The power of the corresponding hypothesis test can be calculated by integrating the non-central t distribution's PDF, or probability distribution function, over the rejection region of our hypothesis test, or equivalently integrating it over the acceptance region of our null hypothesis, and then subtracting the result from 1, or doing 1 minus the probability of a type 2 error, essentially. So it's, as always, easier to understand these things with a picture. So this is a power calculation example with a two-tailed t-test where we actually have terrible power. So the blue area here is 1 minus the power. It is the probability of a type 2 error. The blue curve is the non-central t distribution. The red curve is the null hypothesis. And t-crit is the critical t-value for the null hypothesis with a two-sided t-test at some value alpha. I think I chose 5% here, so alpha's 5%. The two tails are 2.5% then. If I integrate my non-central t distribution over the acceptance region of that hypothesis test, so I integrate it from negative t-crit to positive t-crit, I get that blue area, and that is the probability of a type 2 error, the probability of falsely accepting the null hypothesis when it's not true. 1 minus that is the power of my study. So the fact that that blue area is large means that my power, 1 minus that area, is small. So this is just another example where we have better power. I did the example with really terrible power so that you could see both ends of the area that I've integrated. But here's an example with better power where the non-central t distribution is separated farther from the null hypothesis. And again, the power can be calculated by evaluating that blue area and it's subtracting it from 1. So just last thing I want to mention as I wrap up this video is I know that I've gone over a bunch of math in this video. Don't worry too much about the math. The key point to get is the visualization and the big picture concepts of hypothesis testing and effect sizes and such. R, or whatever programming language you like to use for this stuff, I'm going to show you in R, but you can do these things in Python with the stats models package, you can do them in MATLAB. Whatever language you're using is going to do all of these calculations for you. So you don't need to know the specific form of a non-central t distribution. You don't need to know the specific form of the t distribution. You just need to know generally what they are and when to use them. And with that, I'm going to wrap up this video. Thanks for watching. I'm sorry it took so long, and I hope to see you with the next one where we actually open up a Jupyter notebook and run some of these tests.